everybody, welcome back to chemistry. And so we're continuing on looking at calorimetry, which is interested in understanding the energy changes that occur in chemical reactions. Now, I already talked about one kind of calorimeter that you can use to measure heat changes in chemical reactions, and that's the constant volume calorimeter. Now we have to look at a second calorimeter, which is called the constant pressure calorimeter. And so what that will do is measure heat changes for chemical reactions that occur at constant pressure. So I need to go to the computer and explain that. Constant pressure calorimetry is a little bit different than constant volume calorimetry. And so with constant pressure calorimetry, our goal is to measure energy changes of a chemical reaction when that chemical reaction is at constant pressure. So what we want to do is put the chemical reaction in some kind of device where it can be exposed to atmospheric pressure. And so one easy thing to do is just have the chemical reaction occur in some kind of container. And usually the container used in a lot of undergraduate labs is a coffee cup. And so here we have the constant pressure coffee cup calorimeter. So the way we make sure that this chemical reaction is going at constant atmospheric pressure is as follows. We have the chemical reaction contained in a cup here, and so over the cup we have a really loose fitting cap, which I'm pointing to here, which is called the insulated stopper. And so therefore the reaction will always be exposed to atmospheric pressure. Now, it is possible that your chemical reaction may create volume, and if so, then it may be generating a little bit of pressure. What will happen is that the pressure that is also maybe a little bit generated will leave pretty quickly from this coffee cup, and so we can sort of assume that through the chemical reaction, the pressure over the reaction remains constant. Now, there are a few other things I need to sort of mention that are part of this constant pressure calorimeter. So again, we have this chemical reaction here, and it is going to be inside two nested coffee cups. And so what is the purpose of the coffee cups? Well, the purpose of the coffee cups is as follows. We have a chemical reaction going on inside, and so the heat that is generated from the chemicals, we want all of it to go to the water such that the thermometer picks up any heat changes that occur in the water. So one thing we don't want to have happen is we don't want the heat to be able to leave and get out of the water and get into the environment. So what we have here is styrofoam cups. We have two of them, and they are an insulated container such that heat here is stuck in the water and cannot escape, and therefore all heat will be used to warm the water, and so the temperature change of the water will reflect the heat that is released in the reaction. Also, another thing we don't want to happen is we don't want any heat in the outside getting in to the solution. And so the styrofoam cups, which are very insulating, prevent any heat from the outside getting into the solution. And so there are a couple of other things that you might need. And so one thing you definitely need is a thermometer to record any changes in the water temperature. And then finally, you need maybe some kind of device to stir the reaction that is going on here. And so that is the coffee cup calorimeter. As you can see, it's pretty simple. So one of the things we need to sort of talk about is how we define the system and the surroundings for constant pressure calorimetry, which is done in a coffee cup calorimeter. And so here I just indicate the system is the reaction itself, while the surroundings are going to be the water solution. So let me try to explain that a little bit more carefully here with this example. Let's say that you are interested in figuring out how much heat is released when you add sodium hydroxide pellets into water. How would we set this up in our minds so we can make the calculation of the heat that is released by the sodium hydroxide pellets? And so what will happen is sodium hydroxide will dissolve in the water. The reason why this is happening is because the sodium hydroxide is disassociating into the water. And so what I'm going to do is indicate here that this reaction is occurring, that sodium hydroxide is dissociating into sodium ions and hydroxide ions. Now, one of the things you'll notice is that the water is getting hotter. And the reason is that this chemical reaction is releasing heat or energy into the water. So what we do is we pretend here that this chemical reaction here, which is going on, say, within those pellets there, we think of this as the system. And then the heat is leaving the chemical reaction, the system, and it's going into the water, which is acting as the surroundings. And so the water solution is the surroundings. Okay, so what we can do is write some equations that can help us solve problems. And so one thing we note here is that, as before, the heat of the system, or heat is Q, is equal to the negative heat of the surroundings. So we can substitute here the chemical reaction to be the system here, and we can substitute the water solution to be the surroundings, so I've written that. Now, any heat that is being released or absorbed here in this environment is being released and absorbed at constant pressure. So we can just say, well, the Q of the reaction is really the heat released or absorbed by the reaction at constant pressure. So if we wanted to, we could write QP. So this is going to be equal to any heat released or absorbed by the solution. And of course, when you're relating these heats of the system reaction or at constant pressure to the surroundings and the solution, you have to change the signs. Now, what you'll see is that you can figure out what the heat of the solution is. In other words, we can figure out how much heat the water solution has absorbed or released into the chemical reaction. And that's just going to be equal to the mass of the solution times the specific heat of the solution times the temperature change of the solution, where the temperature change of the solution is just the final temperature of the solution minus the initial temperature of the solution. Okay, so one thing that's really important to know is that when you are doing experiments in a constant pressure coffee cup calorimeter and you figure out what the heat of the reaction is, which is a QP, this is going to be exactly the same value as the enthalpy change of the reaction and not the internal energy change of the reaction. So to explain this a little bit more, let's just step back and think about what a constant volume calorimeter did. So here we have on the left here a constant volume calorimeter. And so you might remember what happens here is that you have some kind of chemical reaction here in the bomb cell, and then maybe it releases its own heat, and maybe it does on its own, maybe it does some work. But here's the problem. When you're in a constant volume calorimeter, all that work will be converted to extra heat. And so here, the heat that is released by the chemical reaction here into the water of the constant volume calorimeter, this heat is going to be QV, which is heat at constant volume. And what that is just the heat that the reaction naturally has added to the work. And so you might remember again, in a constant volume calorimeter, work cannot be done because we're at constant volume. And so the work energy is converted or manifested into additional heat energy to give us QV. So you can see that all the work and the heat of the reaction in the bomb calorimeter is accounted for. And so when we measure this accounting of all the heat and work, which is QV, what we get is the internal energy change of the reaction. Now, for a constant pressure calorimeter, a coffee cup calorimeter, things are a little bit different. And so here we have our coffee cup calorimeter. And so here we have our chemical reaction that is occurring. Now, notice here we are not at constant volume. In other words, in the coffee cup calorimeter, this reaction can have volume changes. And if you have volume changes, that means the system or the reaction can do work on the surroundings, or maybe it's the opposite. The surroundings are doing work on the system. So you can have this chemical reaction in the calorimeter doing work, and it's also either releasing or absorbing heat. And so here we have an equation that accounts for that, in that the total change of the internal energy of the reaction is just going to be equal to the heat of the reaction plus the work of the reaction. Now, here, the heat of the reaction is being done at constant pressure. And so we can rewrite this and say the total internal energy change of the reaction is equal to the heat at constant pressure plus the work. But here's the thing. Yes, this chemical reaction is doing work, but all we're doing is we're just measuring the heat that is generated by the chemical reaction by looking at the temperature change of the water. So when we're just looking at the heat of a chemical reaction and ignoring any work that can be done, then that heat of that chemical reaction is not going to be equal to the change of internal energy of the reaction. Instead, it's equal to the change of enthalpy of the reaction. So in summary, when you carry out a reaction in a bomb calorimeter here, the heat that you measure is the heat of the reaction combined with any work done. And therefore, that heat, which is heat at constant volume, is going to be equal to the change of internal energy of the reaction. On the other hand, when you're at a constant pressure calorimeter, you can have changing volume. That means work will be done in this reaction. But again, the work in this constant pressure calorimeter will not be converted into additional heat. So the heat you measure here is just the heat that is related to the chemical reaction itself, which is going to be equal to the change of enthalpy of the reaction. Okay. So let's go ahead and do some problems that are related to constant pressure calorimetry. And so here is a problem that we have here. When 50 milliliters of 1 mole HCl and 50 milliliters of a 1 mole NaOH, both at 21.5 degrees C, are added to a coffee cup calorimeter, the temperature of the mixture reaches a maximum of 28.9 degrees Celsius. What is the heat produced by this reaction? What is the change of the enthalpy of this reaction? So let me go ahead and go to the board to solve this problem. Okay, so I think what I want to do first is to draw a little picture that sort of describes the problem. That will help me sort of figure out how I'm going to solve the problem. So we have solutions in a constant pressure calorimeter, which could be coffee cup calorimeter. So here is my coffee cup calorimeter, such as it is. I'm just going to leave out the lid and all the other details and just mention what the reactants are. And so it looks like what we're doing is we have 50 milliliters of hydrochloric acid, which is at 1.0 molar. And then to it, we're going to add 50 milliliters of sodium hydroxide, which is at 1.0 molar. And so what we have to do is we have to figure out what the heat is involved when this chemical reaction between sodium hydroxide and hydrochloric acid occurs. And then from that, we can figure out what the change of enthalpy of the reaction is. So first, let me remind you of the chemical reaction that's going on here. So when you mix the HCl with the NaOH, they will mix together. And so what will happen is the HCl, which is an acid, will react with the NaOH, which is a base. And what it'll do is we'll get a neutralization reaction. I'm hoping you can sort of predict the products of the reaction. The products are going to be water and a salt. So for this neutralization reaction, you're going to get some heat generated. Okay, so let me think about this in a different way so I can set up the systems and the surrounding of the reaction. So I'm going to think about this in a different way. So here is our coffee cup again. And so instead of thinking individual solutions, I'm going to think of a total solution of 100 milliliters of solution. And the reason why it's 100 milliliters of solution total is because we have 50 milliliters of HCl and 50 milliliters of NaOH. And so I remind myself what is going on in this 100 milliliters of solution is a chemical reaction which is apparently releasing heat into the solution because the temperature of the solution is increasing. So I'm just going to indicate the chemical reaction here. So we have HCl plus NaOH goes to H2O and NaCl. Okay, so the way I can sort of solve this problem is I can think of here the chemical reaction itself. I'm just trying to draw an oval around this. This chemical reaction itself, we'll think of this as the system. And then we're going to think of everything outside of the chemicals in the chemical reaction. The water solution is going to be the surroundings. So again, because the temperature of the water is increasing, what that indicates is that heat is leaving this chemical reaction and it's going into the surroundings. So heat is leaving the system and going into the surroundings, okay? So what we can do is we can write some equations that can help us solve the problem. So you always know that any heat leaving the system is going to be the same magnitude but the opposite sign of the heat going into the surroundings. So we can write that. Now, what is the system? The system is this chemical reaction, this neutralization reaction. So it's the heat of the reaction is the system is equal to negative Q of the surroundings. So what are the surroundings? Well, the surroundings are the water solution. So we want to have a Q of a surroundings, and so let's break this into individual masses and specific heats and temperature changes. And so to do that, you probably already know here that Q is going to be equal to the mass of the solution. Here we're looking at the solution itself, and we're going to be considering the mass. And so we don't need a general heat capacity to solve this problem. We need a specific heat capacity to solve this problem. So I'm going to use a little c here, not a big C. And then we have a temperature change, so I'm going to put delta T here. So we can substitute this into Q of the surroundings. So it's going to be equal to M times C times delta T. And so let me just remind myself that this is the surroundings. Okay. And so now I think we can go ahead and plug in numbers and figure out what the heat of the reaction is. And so here, the mass of the water, how do we figure that out? Well, we have 100.0 milliliters of this water solution. And I think the problem tells you to assume that the density of this water solution is 1.00 grams per mil. So therefore, we have 100.0 grams of this solution. So it's 100.0 grams of this solution. And so the specific heat of the water solution, we assume it to be the same as water, which is going to be 4.184 joules over gram degree Celsius. And then finally, you have to figure out the temperature change. Okay, so the temperature change, let me work that up here. So we're trying to find a temperature change, a delta T, and so that's going to be equal to the final temperature minus the initial temperature. So what is the final temperature there? The final temperature, it looks like it's going to be 28.9 degrees. The initial temperature is 21.5 degrees. And so it looks like the temperature change, I worked it out before, is 7.4 degrees Celsius. And so I'm going to put this here, 7.4 degrees Celsius. Okay. So now what we can do is find the heat of the reaction. So we find the heat of the reaction. There we go. And so we multiply all these numbers together. And so what I got when I did this earlier was negative 3,096.16 joules. That's what I got in my calculator. Okay, let's just confirm that this should be joules. So we can see grams cancels out here, degrees C cancels out. So we didn't cancel out joules, and so yeah, we would expect joules in our answer. So if we round this to correct number of significant figures, what I get is negative 3.1 times 10 to the 3, there we go, joules. Now, what is the enthalpy change of the reaction? Well, the enthalpy change of the reaction is just going to be equal to the heat at constant pressure. And as I described earlier, if you have a chemical reaction that is occurring at constant pressure, that heat of reaction will be the heat at constant pressure. So here we have the heat of the reaction. It's going to be equal to the heat at constant pressure, which is going to be equal to the enthalpy change of the reaction. And so this should be the same value. So the enthalpy change of the reaction should be negative 3.1 times 10 to the 3 joules. Okay. All right, so let's move on to the next problem. When solid ammonium nitrate dissolves in water, the solution becomes cold. This is the basis of an instant ice pack. When 3.21 grams of solid ammonium nitrate dissolves in 50 grams of water at 24.9 degrees Celsius in a constant pressure calorimeter, the temperature decreases to 20.3 degrees Celsius. What is the enthalpy change in joules per mole of ammonium nitrate for this reaction? Okay, so let me go ahead and draw a picture of what I think is going on here. And so here is our constant pressure coffee cup calorimeter. And so this time it looks like we're adding a solid salt to 50 grams of water and it's cooling down the water. So let me here indicate the water here. It's given to us in grams, which would be 50 milliliters. So let me just indicate that this is 50.0 grams of water. Okay. So to this 50 grams of water, we're adding 3.21 grams of ammonium nitrate. So let me just kind of draw that into our picture here. So we have 3.21 grams of ammonium nitrate. Okay. So what I want to do to sort of make my life a little bit easier is sort of simplify this picture a little bit. So think of it this way. We'll assume that the mass of the solid adds to the mass of the water to make a total mass of solution. So the total mass of solution is going to be what? 53.21 grams of solution. Now, what is the chemical reaction that is going on? The chemical reaction is going to be the dissociation of ammonium nitrate into water. So let me draw this here or write this out so we can see it a little bit more carefully. So here is ammonium nitrate. It's going to be in the solid state. And then when we add to water, it will dissociate to produce ammonium and nitrate ions into the water. So this is going to be NH4 plus NO3 minus. And so this is going to be the chemical reaction. So let me just indicate this is the chemical reaction. So this is going to be occurring in the water. So I'm going to draw this real small here. So as ammonium nitrate is dissociating into ammonium plus nitrate. So we're going to think of this chemical reaction here as the system. And then what we're going to do is think of the water solution. This is mostly a water solution, so let me just indicate there's water here. We're going to think of that as the surroundings. Now, there is a heat change between system and surroundings, but it's a little maybe different than what you might expect. So if you read the problem, what you'll see is that when you add the ammonium nitrate salt to the water is cooling down. So what does that tell you? It tells you that heat must be leaving water and going into the chemical reaction. So here the Q is a little bit different. Here we're going an arrow here into the system. This is the heat going into the system. Again, it's leaving the water, cooling it down, and going into the chemical reaction. Okay, so now we can go ahead and throw up some equations in that we have the Q of the system is equal to negative Q of the surroundings. All right, and so the Q of the system is the Q of the reaction, which is the dissociation of ammonium nitrate into ions and water, is going to be equal to the negative Q of surroundings. And again, Q is going to be equal to the mass times the specific heat times the change of temperature. So it's going to be negative M times C times delta T of the solution. All right, so we can continue on. Let's go ahead and plug in some numbers. So the Q of the reaction is going to be equal to negative M, and so we want the total mass of the solution. So here we add the mass of the water and the ammonium nitrate salt. We assume that they're adding together to form a larger mass, and we need to account for any temperature changes in the total mass of the solution. So it's going to be 53.21 grams times a specific heat capacity for the solution, which we assume to be the same as water. So that is going to be 4.184 joules per gram degrees Celsius times the temperature change. Let's work that out. So delta T is going to be equal to T final minus T initial. And so what is the final temperature in this problem? It looks like it cooled down, so the final temperature is 20.3 degrees Celsius. The initial temperature is higher, it's 24.9. So when I worked this out earlier, the temperature change I got was negative 4.6 degrees Celsius. So we're going to put this here, negative 4.6 degrees Celsius. So you can multiply these numbers together, and so this is going to be the Q of the reaction. So when you multiply the numbers together, I got 1024 joules. That's more than enough significant figures for now. This negative sign multiplies with this negative sign. They cancel out. So this should be a positive 104 joules. Okay. Now, what we're trying to do is we're trying to find an enthalpy change here of the reaction, but we have to be careful. We don't want the enthalpy change so much in joules. We want it in joules per mole of ammonium nitrate. So we're going to have to figure that out, which isn't so bad. So we have the Q of the reaction. So the Q of the reaction, if this reaction is occurring in a constant pressure calorimeter, is just going to be equal to the heat at constant pressure, which is going to be equal to the enthalpy change of the reaction. And so we now know that the enthalpy change of the reaction is going to be that value. The enthalpy change of the reaction is going to be positive 1024 joules. But again, the problem is this. We don't want an answer in joules. We want the answer in joules per mole. So what do? So first off, let me fix this funky looking J here. Okay, so there we go. J is fixed. Okay, so here's how I think about it. So where this energy went to was it went into the 3.21 grams of ammonium nitrate. So again, this is energy that went into that specific mass of ammonium nitrate, and then once that mass of ammonium nitrate got that energy, it just dissociated into ions. And so we can write here, well, it's 1024 joules per 3.21 grams of ammonium nitrate. Now, what we can do is use this fraction and multiply it by the molar mass of ammonium nitrate, and I think what you'll see is then you will find that the grams of ammonium nitrate will cancel, and we're left with an answer in joules per mole. So let's go ahead and do that. So we are given the molar mass of ammonium nitrate. It's 80.043 grams per, let me just be complete here, ammonium nitrate over 1 mole of ammonium nitrate. And you can sort of see now that the grams of ammonium nitrate cancels out. And so now what we're left with is an answer in joules per mole. So it's going to be something in joules per mole because they didn't cancel out. And I think if you did the math, you would get that number I have there on the screen, and that's rounded to correct number significant figures. So the answer is going to be 2.55 times 10 to the 4 joules per mole. Okay, well, thank you for listening to that, and we'll see you next time.